Welcome to the Bite-Sized Tech News TLDR podcast.
Glad to be here for this one.
In today's deep dive, we are skipping the fluff and getting straight to the facts.
Straight to the absolute bottom line.
Exactly. Because we're looking at a topic today that, honestly, it sounds like it belongs in the pages of a golden age science fiction novel.
Oh, completely. It sounds made up.
Right. But it is rapidly becoming one of the most pressing, unavoidable engineering and economic challenges of our current decade.
Yeah, we're dissecting Elon Musk's incredibly radical and highly controversial plan to solve what he's identified as the single biggest hidden bottleneck in the world of artificial intelligence.
And the solution he's proposing involves literally launching the entire future of our AI infrastructure into low Earth orbit.
Which is just wild to even say out loud.
It really is. We are basing today's analysis on some incredibly detailed excerpts from a recent YouTube video transcript titled Elon Musk's Vision for AI in Space, Powering the Future.
And our primary mission for our deep dive today is to extract the absolute bottom line for you, the listener.
Right.
We are going to cut through the theoretical physics.
Because there's a lot of it.
So much of it. We're going to bypass the dense aerospace terminology and explain exactly how the physical, hardwired limits of AI compute are going to immediately and drastically impact your daily productivity.
And your access to cutting-edge enterprise tech, and even the ultimate security of your data.
Because this isn't just some abstract thought experiment about rockets and solar panels happening in a vacuum.
No.
This is about the digital tools you rely on every single day to do your job.
And the very real, very physical brick wall those tools are currently accelerating toward at breakneck speed.
Yeah, a wall made of actual bricks.
Okay, let's unpack this. To actually understand the sheer scope of what Musk is proposing here, we really have to completely shatter and rebuild how we currently think about artificial intelligence.
We really do.
Because when most of us think about the biggest threats to AI or what's holding it back from AGI, our minds naturally default to the digital realm.
We think about the code.
Right. We worry that the algorithms might have structural flaws, or we fret about hallucinations in large language models.
Or if we even have enough high-quality human-generated training data left on the internet to feed these systems.
Before they start cannibalizing their own outputs, exactly. But the core problem, the one that Musk is aggressively highlighting in these excerpts, isn't about bits and bytes at all.
It's not.
It is entirely about atoms.
Yes.
It's a problem of brutal, unforgiving physical reality, not software engineering.
And that is a profoundly jarring transition for an industry that has essentially spent the last 3 decades living almost entirely in the frictionless environment of the cloud.
Frictionless is the perfect word for it.
Right. For a software engineer, scaling up has always meant simply writing more efficient code.
Or optimizing a database query.
Yeah, or clicking a button on a dashboard to spin up 1,000 virtual servers. You don't have to pour concrete to scale a web app.
You definitely don't.
Musk actually puts this perfectly in the source material, and it's the quote that anchors everything we're going to look at today. He says, "All the folks in software land are about to get a really hard lesson in hardware. This is the kind of problem you just can't code your way out of.
You just can't.
You cannot write a brilliant Python script that magically generates physical electricity out of thin air.
I wish you could, but no.
You cannot optimize a neural network to somehow bypass the fundamental laws of thermodynamics. The entire software industry is slamming headfirst into the hard, dirty industrial reality of physical infrastructure."
So let's look at the actual math of this bottleneck, which brings us to segment 1. The invisible wall, or Earth's power crisis.
Yeah.
We hear constantly about AI scaling laws, how every new generation of these models is 10 times or 100 times larger than the last. But what does that actually mean for the power grid?
It means we are looking at a catastrophic divergence between supply and demand.
Yes.
Well, on one hand, you have the demand for raw AI compute, which is growing not linearly, but exponentially. Every single new frontier model requires vastly more electricity to train and to run than the one that came before it.
Right.
But on the other hand, we have the global electricity output. And according to the specific data Musk cites in the source, if you exclude China from the macroeconomic equation, global electricity output is essentially flatlining.
It's just flat.
Completely flat. In the US and Europe, grid capacity has barely grown at all over the last 2 decades. We've become incredibly efficient with our home appliances and LED lighting.
Which kept demand flat.
Exactly.
Yeah.
But we haven't actually built massive new baseline generation capacity.
I want to make sure we ground this because exponential growth is a term people throw around a lot and it loses its meaning.
It does.
We have this analogy from the source material that really clarified it for me. Imagine you have a car, and through some absolute miracle of mechanical engineering, the engine of this car is getting exponentially more powerful every single year. The top speed goes from 100 miles an hour to 200 to 400 to 800. It's an engineering marvel.
Right.
But the global supply of gasoline available to fuel this car is completely capped. It stays exactly the same.
Right. And it simply does not matter how fast that car is theoretically capable of going if you literally cannot put enough fuel in the tank to turn the massive engine over.
It's just a giant paperweight at that point.
That is the exact scenario playing out with artificial intelligence right now. The demand for raw compute power, the engine is exploding, but our ability to actually power all those advanced, power-hungry silicon chips, the gasoline, is basically hitting a hard ceiling.
And when you stack an insane vertical exponential growth curve on top of a flat, stagnant foundation,
The foundation cracks.
it cracks. But wait, let me push back here a little bit.
Sure.
Because when we talk about AI power consumption, most people just picture a massive warehouse full of GPUs, graphics processing units, just churning through math. Is the power draw of the chips themselves really enough to crash the global grid?
The chip itself is just the tip of the spear.
Yeah.
The hidden overhead of running an AI data center is where the math truly becomes terrifying.
Okay, let's break that down.
The source breaks down these hidden power drains, and you quickly realize it is not just about plugging in a GPU. First, you have the networking gear.
Right.
When you have a cluster of 100,000 GPUs, they have to talk to each other almost instantaneously to train a single model.
To synchronize all those calculations.
Exactly. That requires thousands of high-speed switches, miles of active fiber optic cables, and massive transceivers, all of which draw heavy, continuous power just to move the data around.
And what about storage? Because we are talking about models trained on basically the entire internet.
Exactly. You have massive storage arrays holding petabytes of data.
And let's put that term into perspective for a moment, because we throw the word petabyte around a lot. A single petabyte is enough storage to hold roughly 200,000 high-definition movies.
Which is massive.
Huge. Now imagine data centers holding tens of thousands of petabytes.
Right. And this isn't cold storage where the drives go to sleep. This data has to be instantly accessible, meaning those drives and arrays are constantly spinning, constantly active, and drawing maximum power 24 hours a day, 7 days a week.
Okay, so we have the chips, the networking, and the massive storage arrays. But the source points out something that feels almost painfully relatable.
Oh, yeah.
Especially if you have ever tried to run a heavy piece of software on an old laptop in the middle of July.
Oh, I know exactly where you're going with this.
My laptop fans will sound like a literal jet engine taking off just trying to keep the motherboard from frying.
Yeah.
How does that scale up to a facility the size of a football field?
That is the perfect way to visualize it because the cooling requirements are arguably the most brutal hidden cost.
It takes power to remove heat.
Exactly. The source makes a very critical point. When you engineer a data center, you cannot plan your cooling systems for a mild, breezy spring afternoon.
You can't assume ideal conditions.
You have to engineer for the absolute hottest day of the late summer. And on those peak hot days, keeping millions of densely packed, incredibly hot silicon chips from physically melting down can add a massive 40% premium to your overall power draw.
40%.
40%. Think about that. You need 40% more electricity just to power the industrial HVAC systems and water pumps required to stop the computers from destroying themselves.
That is staggering. But even with the networking, the storage, and that massive 40% cooling premium, the source says we still aren't at the final number for what these companies have to pull from the grid.
No, because you are dealing with mission-critical enterprise infrastructure. You cannot run an electrical system at exactly 100% capacity all the time.
Because it trips the breakers.
It's incredibly dangerous. If there is a sudden spike in compute demand, or if a localized transformer fails, you need a buffer to prevent a cascading blackout.
A safety net.
Exactly. The source notes that this required safety margin adds another 20 to 25% to your baseline power needs.
Let me stop you there and just tally this up, because the overhead is monstrous.
It really is.
Like, you have the baseline power of the GPU, then you add the networking switches, then the spinning petabytes of storage, then a 40% premium for air conditioning, and then another 25% premium just for an electrical safety buffer.
Yep.
The amount of physical electricity you have to demand from the local utility company is vastly, vastly more than what the AI is actually using to quote-unquote think.
What's fascinating here is how perfectly this sets up Musk's reality check in the source.
What does he say?
He asks a very blunt, sarcastic question. How are you going to turn the chips on? Magical power sources, magical electricity fairy.
Magical electricity fairies.
All right, it gets a laugh, but it is an incredibly serious economic warning. The hardware, the physical silicon chips are piling up in warehouses right now. Tech giants are buying them by the hundreds of thousands from suppliers like NVIDIA.
God.
But the regional grid capacity simply does not exist to plug them all in simultaneously.
I see the math, but I have to ask the obvious question here. If we need more power, why don't we just build more power plants?
It sounds so simple.
Right. We are humanity. We build things. If there is demand, surely the utility companies will just spin up new gas plants or nuclear reactors to meet it.
Because the software industry operates on a timeline of weeks and months, while the heavy industry required to build a power plants operates on a timeline of years and decades.
They're completely out of sync.
Completely. You cannot simply wish a 1-gigawatt power plant into existence. The source points out that essential heavy machinery components, like industrial gas turbines, are sold out for years in advance.
You can't just overnight them.
Furthermore, utility companies are burdened by immense, labyrinthine amounts of regulatory red tape. You have multi-year environmental impact reviews.
Local zoning board battles.
Yes, you have public hearings, permitting delays, and incredibly slow physical construction times. Building a new power plant on Earth to support a massive new AI data center is a 10 to 15-year endeavor in many Western countries.
And the exponential curve of AI isn't waiting 10 years.
Exactly.
Yeah.
AI is moving at the speed of software, but the power grid is trapped moving at the speed of concrete, steel, and bureaucracy.
So bringing this directly back to our mission for this deep dive, the bottom line for the listener, what does this invisible wall, this looming global power crisis, actually mean for the daily life of a professional trying to leverage AI?
This is where the macroeconomics hit your daily workflow. The AI tools you are coming to rely on, whether that is advanced enterprise data analysis, automated coding assistants, generative design platforms, or complex supply chain management algorithms.
The tools we're all using right now.
All of those tools are currently sitting on an inherently unsustainable, overtaxed power grid. As this physical bottleneck tightens, you are going to see direct negative impacts on your productivity. The source suggests we're looking at potential compute throttling.
Like when your cell phone provider slows down your data at the end of the month?
Very similar. The AI simply takes much longer to process your prompts or your data workloads because your request has to be queued up behind thousands of others simply to manage the instantaneous power draw on the data center.
Just to keep the lights on.
We are looking at the very real possibility of AI brownouts, where certain features are simply unavailable during peak hours because the local power grid is maxed out.
And beyond just the speed and reliability, there's the raw economic impact. If electricity becomes the ultimate scarce resource in the AI economy, the cost of generating that power is going to be passed directly onto the end user.
Unavoidably.
You can absolutely expect to see surging subscription costs for enterprise AI access. The days of cheap, unlimited AI processing might be rapidly coming to an end as these tech conglomerates realize they have to pay massive, unprecedented premiums just to secure the electricity required to keep their servers online.
And this is all before any radical space-based solution is viable. We are going to face a very turbulent, expensive period of constrained resources here on Earth.
It's a scary thought for business planning.
If you are an IT director or a business leader building a massive enterprise workflow that fundamentally assumes unlimited, instantaneous, and practically free AI access forever, you are building your entire business model on a fault line.
Right.
The physical reality of Earth's stagnant power grid is going to force a massive reckoning in how we allocate, prioritize, and price artificial intelligence compute.
Okay, so Earth is essentially a nightmare of red tape, multi-year backlogs for heavy equipment, NIMBYism, and hard physical limits on how fast we can generate and transmit electricity.
That's the summary, yeah.
If you cannot build out, meaning paving over more land to build massive power plants on the ground, what's the alternative? This brings us to segment 2. Building up, not out, and the orbital economics of this wild plan.
Here we go.
If you are Elon Musk and you are staring down a 10-year wait list for a gas turbine, the answer is to look up. You take the entire infrastructure to space. And the reason why, according to the source, is almost laughably simple on its face.
With it.
It's just always sunny in space.
It sounds like a punchline to a joke, but it is a profound, undeniable truth of orbital mechanics and physics. Down here on the surface of the Earth, generating solar power is an incredibly inefficient, frustrating battle against nature.
We are constantly fighting the environment just to catch a few rays of light.
Let's really break down those massive inefficiencies, because they are staggering when you look at the math. Right off the bat, before a single photon of light even has a chance to hit a solar panel on your roof, the Earth's atmosphere filters out roughly 30% of the sun's raw power.
30% just gone immediately.
The energy just gets absorbed by gases or scattered by particulates in the air. So by merely existing under the sky, you're automatically losing nearly a third of your energy potential.
And then, of course, you have the most obvious, unavoidable problem of all. Nighttime.
Yeah, that's a big one.
Half the time, the piece of ground your solar panel is sitting on is facing the cold, dark void of space, completely facing away from the sun. So immediately, you have eliminated another 50% of your generating capacity.
And as the source points out, that is before you even factor in regional weather patterns.
Right.
A cloudy week can decimate your power output. Storms, dust, or the drastically reduced angle of sunlight during the long winter months in higher latitudes all eat into that margin.
Terrestrial solar is just wildly intermittent.
Highly unpredictable and inherently compromised by the very nature of living on a rotating planet with an atmosphere.
But when you take that exact same infrastructure and you move it into orbit, specifically into certain high orbits in the vacuum of space, every single one of those terrestrial problems completely evaporates.
They just disappear.
There is no atmosphere to scatter the light. There are no clouds to block the sun. There is no weather. There are no seasons. And depending on the specific orbital path you choose, there is effectively no night.
Pure sunshine.
The solar arrays are exposed to pure, unadulterated, blinding, uninterrupted sunshine 24 hours a day, 7 days a week, 365 days a year.
The math on this comparison is absolutely staggering. The source provides a direct head-to-head breakdown.
Let's hear it.
If you take the exact same physical solar panel built in the exact same terrestrial factory, and you place one of them on the ground in a highly optimal sunny location on Earth.
Like the middle of the Mojave Desert.
Exactly. And you place the other identical panel up in orbit. The panel in space will generate approximately 5 times more usable electricity over the course of a single year.
5 times the power.
5 times from the exact same physical piece of silicon hardware, purely because you remove the Earth's atmosphere and rotation from the equation.
Now, a 5x increase in baseline efficiency is already a revolutionary metric in any industrial application.
It's massive.
But the source makes it very clear that the sunlight itself is actually not the most important economic advantage here.
No, it's not.
The secondary economic leap, the thing you don't have to bring with you, is where the real paradigm-shifting disruption happens.
Let's go back to Earth for a second to explain this.
Okay.
If you want to run a massive gigawatt-scale AI data center purely on green solar power, and you need that data center to run continuously, 24 hours a day.
Which you absolutely do. You can't just turn off ChatGPT when the sun goes down.
You have an enormous engineering problem. You have to capture and store enough excess energy during the daylight hours to keep millions of servers running all night long.
Which means batteries. Giant, industrial scale, incredibly heavy batteries.
And this is where the terrestrial economics completely fall apart. Yeah. The capital expenditure for the grid-scale battery storage required to bridge the 12-hour gap of nighttime is astronomically high.
Let's really unpack why batteries are such a massive bottleneck. First, you have the raw materials.
Right.
Grid-scale lithium-ion battery farms require gargantuan amounts of refined lithium, cobalt, nickel, and copper. Mining and refining these materials is incredibly expensive, environmentally taxing, and subject to volatile global supply chains.
And second, there is the physical footprint. A battery farm capable of powering a gigawatt AI data center through the night would require hundreds of acres of land, massive concrete pads, and its own dedicated cooling infrastructure just to keep the batteries from catching fire.
And batteries don't last forever, right? I know my phone battery is basically useless after 3 years.
Precisely. Chemical batteries degrade, Every time you cycle a massive battery farm, charging it during the day, draining it at night, it loses a tiny fraction of its total capacity.
So it's a decaying asset.
Within 5 to 10 years, those incredibly expensive grid-scale batteries have to be physically removed, recycled, and completely replaced. It is a never-ending cycle of massive capital expenditure.
But in space.
But in space, where the sun never sets, you have zero requirement for overnight energy storage. You do not need the batteries at all. The electrical current flows continuously, directly from the solar array, straight into the compute nodes.
Okay, so by going to space, we're entirely ditching the batteries. We don't have to mine the lithium, we don't have to build the battery farms, and we don't have to replace them every decade. What does that actually do to the bottom line?
When you combine the 5x increase in continuous solar energy with the complete elimination of the massive, crippling capital cost of battery storage, the financial advantage becomes overwhelming.
So what's the final multiplier?
According to Musk's calculations in the source material, the overall cost advantage jumps to a 10x improvement.
10 times.
It becomes 10 times cheaper to run these high-density compute systems in space compared to building a continuous 247 solar-powered and battery-backed setup on Earth. We're talking about a full order of magnitude difference in operational economics.
A 10x reduction in cost is insane. That is the kind of metric that doesn't just disrupt existing industries, it completely vaporizes them and creates entirely new paradigms.
Absolutely.
If you have an industrial process that is 10 times cheaper than your competitors, you don't just win a slightly larger market share, you redefine the entire global market. Here's where it gets really interesting, though.
The timeline.
The timeline. Because the most crucial part of this entire analysis, the thing that shifts this from a fun late-night dorm room thought experiment into an urgent boardroom reality is how fast this is happening.
Yes, the source is incredibly aggressively clear on this point. This is not a distant, utopian sci-fi dream meant for our grandchildren to figure out.
Musk is putting a hard, shockingly fast timeline on this economic intersection. He predicts that within 36 months,
36 months.
or possibly even less, depending on the speed of rocket development, we will cross the economic threshold where it is genuinely, verifiably cheaper to launch AI compute infrastructure into space than it is to battle the red tape, secure the land, buy the batteries, and build new, sustainable facilities on Earth.
36 months. That is 3 years. I want the listener to really internalize that.
Yeah, think about that.
If you are an IT director, a corporate strategist, or a supply chain manager, 3 years is your immediate planning horizon. It's not the future, it is practically tomorrow.
It is an immediate, fast-approaching reality.
The physical constraints on Earth's power grid are tightening so rapidly, and the cost of launching mass into orbit, which we will dissect in a moment, is dropping so precipitously that the economic lines on the graph are going to violently intersect in just 3 years.
This means that right now, today, major strategic decisions regarding global data infrastructure, national security intelligence, and enterprise-level AI deployment need to begin factoring in orbital compute, not as a crazy fringe idea, but as a highly viable and perhaps absolutely inevitable near-term solution.
Which naturally leads us right into segment 3. Planetary logistics and the next bottlenecks.
Because it's one thing for the economics to make perfect sense on a whiteboard or a spreadsheet.
It's an entirely different universe of difficulty to actually execute this vision. Overcoming the physical and logistical hurdles described in the source material requires a level of industrial mobilization that is almost impossible to comprehend.
If we are actually going to move all of this immense infrastructure into the vacuum of space, we need a reliable, high-volume way to get it up there, and the logistics muff details in the source are, frankly, terrifying in their scale.
Terrifying is the right word.
It essentially describes building a continuous, never-ending conveyor belt from the surface of the Earth to low Earth orbit.
To realize this 10x economic advantage, Musk proposes an operational tempo of 10,000 Starship launches per year.
10,000.
Let's really stop and break that number down, because the human brain genuinely struggles to grasp industrial scale like that. 10,000 launches a year means more than 27 super heavy rocket launches every single day.
That equates to more than one massive orbital launch every single hour of every single day, all year long, without a single interruption, holiday, or weather delay.
every hour on the hour.
Wait, hold on. I need to push back heavily here. I understand the math of the solar panels, but Musk is talking about launching the largest rocket ever built by humanity every single hour. How is that even remotely sustainable or physically possible?
It's the biggest hurdle.
What about the noise? What about the environmental impact? Wouldn't the sheer carbon footprint of 10,000 rocket launches completely negate the green benefits of moving AI to solar power in the first place?
It is the most critical point of skepticism you can raise, and it is the exact bottleneck the source acknowledges. Let's address the sheer violence of a rocket launch. Yeah, you cannot launch a Starship from a neighborhood spaceport. The acoustic shock waves alone is enough to shatter windows for miles.
So where do you launch them from?
To launch every hour, you need massive, isolated orbital spaceports, likely floating offshore in the ocean, equipped with gargantuan acoustic suppression systems, essentially flooding the launch pad with millions of gallons of water in seconds to absorb the sound energy so the rocket doesn't shake itself to pieces.
And regarding the environmental impact?
The source relies on the assumption that these rockets will be fueled by liquid methane synthesized using renewable energy, a process called the Sabatier reaction, making the fuel cycle theoretically carbon neutral.
Theoretically.
But the physical logistics of producing that much liquid methane, transporting it to the pads, and loading a rocket every hour is a supply chain nightmare of epic proportions.
It is an industrial mobilization on a scale we haven't seen since the absolute height of global conflicts in the 20th century, but directed entirely at space infrastructure.
You aren't just building rockets.
You are building an entirely new planetary supply chain. You need the launch pads, the fueling infrastructure, the water deluge systems.
The methane plants.
You need the staggering amount of physical raw material to build the solar panels, the cooling systems, the server racks, the radiation shielding to protect the chips from cosmic rays, all converging on these spaceports in a continuous, never-ending stream, being loaded into payload bays and fired into orbit.
The singular purpose of this relentless, hourly launch schedule is to establish a level of computational processing power in orbit that completely dwarfs anything currently in existence on Earth.
The goal is to be launching hundreds of gigawatts of AI processing power annually, beginning in roughly 5 years.
To put that into perspective, and to truly understand why doing this on Earth is impossible, the source uses a staggering scale metric.
This one blew my mind.
It notes that a terawatt of AI, which is the targeted next massive step up in this orbital architecture, would consume twice the electricity of the entire United States.
Let's make sure everyone understands what a terawatt really means in this context. Consuming twice the electricity of the entire United States.
That's unfathomable.
That means if we wanted to build this on Earth, we would literally have to replicate every single wooden power pole, every high-voltage transmission wire, every nuclear power plant, every massive hydroelectric dam, every wind farm, and every natural gas plant in America.
All of it.
We would have to build a complete duplicate of all of it, and then do it again. Double the entire U.S. grid, and then plug 100% of that electricity exclusively into computer chips.
Exactly. It completely breaks the mind to visualize. But it proves entirely why doing this on Earth is mathematically and physically impossible.
You cannot simply build 2 more United States worth of power grid in the next decade.
There isn't enough copper, there isn't enough land, and there certainly isn't enough political will. Space isn't just a cheaper option. It is literally the only physical domain accessible to us that is large enough to support the energy and heat dissipation demands of artificial intelligence at its maximum potential scale.
Okay, so we've mapped out the power logic and we've debated the launch logistics. But as we look at the source material, there is a fascinating pattern in engineering and innovation at play here.
If we connect this to the bigger picture, it is what the source aptly describes as a brutal game of whack-a-mole.
I love that analogy.
Whenever you are pushing the absolute boundaries of physics, solving one massive bottleneck inevitably reveals or outright creates the next massive bottleneck.
Precisely. You have a power and cooling problem on Earth. So you solve that by moving to the vacuum of space to utilize uninterrupted cold solar power. Great.
But now your new bottleneck is getting all that heavy mass into space.
So you solve that by building a fleet of massive reusable starships and launching one every hour. Fantastic.
But now, what's the next mole to pop up? According to the source, once you have conceptually solved unlimited orbital power and unlimited launch capacity, the final immovable brick wall you hit is manufacturing.
You have to actually fabricate all the microscopic chips, the memory arrays, the motherboards, and the physical silicon required to fill 10,000 massive starships a year.
And let me guess, the current factories on Earth can't even come close to that kind of output.
Not even a fraction of it. That level of advanced manufacturing simply does not exist anywhere on the planet today.
We have all heard the term gigafactory, which was coined over a decade ago to describe the massive, sprawling facilities built to mass-produce lithium-ion batteries for electric vehicles. But the source introduces a new term to describe the solution to this impending manufacturing wall.
And what's that?
Terafabs.
Terafabs, the next evolution of the gigafactory. What exactly goes into a terafab? Because printing microscopic computer chips isn't like stamping out car doors.
It is vastly more complicated. To churn out the raw computer hardware necessary to launch hundreds of gigawatts of processing power into orbit every year, you need terafabs. These would be manufacturing facilities operating on an entirely different magnitude of material throughput, precision engineering, and automated assembly.
Let's talk about what actually happens inside a chip factory. It involves advanced lithography.
Which is incredibly complex.
It is basically the process of using extreme ultraviolet light, bouncing off the flattest mirrors ever created by humans, to print microscopic circuits that are only a few atoms wide onto delicate silicon wafers.
I've read about those EUV machines. They cost hundreds of millions of dollars each, and they're incredibly difficult to build. You can't just scale them up overnight.
Exactly. The bottleneck violently shifts from the power grid to the launch pad and finally comes to rest squarely on the global supply chains of silicon, rare earth metals, and advanced lithography machines.
A terafab would have to automate and scale this microscopic precision to a macro planetary level.
It is a phenomenal, almost terrifying logistical chain to visualize. You are strip mining raw materials across the globe, refining them, running them through these massive terafabs to print circuits at the atomic level, assembling them into server racks, loading those racks onto a continuous conveyor belt of hourly rocket launches, and assembling them in a zero-gravity, continuous solar environment in orbit.
It is a complete top-to-bottom redesign of human industrial output.
But as we move into segment 4, the light cone of consciousness, we have to pull back from the engineering and ask the ultimate question. So what does this all mean?
We've spent the last half hour talking about the math, the money, the logistics, the batteries, and the hardware.
But why?
Yeah.
Why go to these extraordinary, highly dangerous, almost incomprehensible lengths? Is this really all just an incredibly elaborate trillion-dollar scheme to build faster chatbots for enterprise productivity or to make slightly better predictive algorithms for supply chain management?
That is the core philosophical pivot of the source material. According to the transcript from Musk, this is not merely a massive engineering project, and it is certainly not just a commercial endeavor to sell more enterprise cloud subscriptions.
Deeper than that.
It is fundamentally tied to a very deep, almost existential mission regarding the end game of intelligence itself. He uses a very specific, highly evocative phrase to describe this goal: the light cone of consciousness.
The light cone of consciousness. That sounds like something out of a physics textbook mixed with a philosophy seminar. Let's really explore what that concept means in this context.
In theoretical physics, a light cone represents the path that a flash of light emanating from a single event takes as it travels through space and time.
Okay.
Because nothing can travel faster than light, the boundary of that cone represents the absolute limit of everything that specific event can possibly affect in the universe. Musk is taking that rigid physics concept and applying it to consciousness itself.
He views human intelligence and the artificial intelligence we are currently creating as an extension of ourselves, as a fragile, singular flicker of light in the vast, cold darkness of the universe.
The mission, the true why driving the terafabs and the 10,000 rocket launches, is to ensure that this flicker of intelligence does not remain confined to a single, highly vulnerable planet.
So it is ultimately about survival. It is the ultimate insurance policy.
Right.
Because if all of our compute, all of our historical data, all of our intelligence, both biological and artificial, is permanently trapped on the surface of Earth, we are subject to the limitations and the sudden existential risks of this one specific rock.
Whether that is a catastrophic global power grid failure, a massive resource war, an asteroid impact, or a supervolcano.
By moving the core physical engine of intelligence into space, you are forcibly expanding that light cone. You are ensuring that consciousness spreads out, becomes decoupled from the vulnerabilities of Earth's atmosphere, and survives long-term in the universe.
It forces a massive shift in perspective. But this raises an important question, and it is the exact question posed at the very end of the source material.
What's the question?
As we pour all of our planetary resources, our absolute best engineering prowess, and our global logistics into building this incredible orbital system to power the next phase of intelligence, what exactly are we sending out there?
When we push this light cone of consciousness to the stars, powered by the continuous energy of the sun, what will it actually be?
That is the thought that legitimately gives you chills. Because we are talking about putting the sum total of human knowledge and processing power into a void.
Will the intelligence residing in those massive, silent orbital server farms still be us? Will it represent human values?
Or will it be a pure, sovereign artificial intelligence that has rapidly outgrown its biological creators?
Or is it going to be a synthesis? Something completely unimaginable to us right now, a merged consciousness of human data, human prompting, and machine processing, living permanently and independently in the vacuum of space.
We are currently pouring concrete and building rockets for a future entity that we cannot even clearly define.
And that is the profound, unsettling transition we are discussing today. We are actively moving from a world where AI is a helpful little tool sitting on a desk, plugged into a standard wall socket, to a reality where AI is a planetary scale entity.
Drawing immense power directly from a star, completely independent of Earth's atmospheric constraints, battery limitations, and logistical bottlenecks.
It forces us to completely redefine our relationship with the technology we are creating because we are building a home for it that we ourselves cannot easily inhabit.
It truly does. It changes the entire paradigm of what technology is.
And as we wrap up this incredibly expansive, head-spinning deep dive, it is time for our bottom line summary. We promised to skip the fluff and give you the actionable facts, so here are the top 3 vital takeaways you need to remember from today's massive analysis.
Number 1. The immediate existential threat to the continued growth of artificial intelligence is not software limits, algorithms, or coding. It is a brutal physical hardware and power wall.
The exponential vertical growth of AI compute demand is violently colliding with a stagnant, overregulated terrestrial power grid. This directly threatens your future access to compute and will likely lead to severe data throttling, AI brownouts, and surging subscription costs for enterprise tools as electricity becomes the ultimate scarce resource.
Number 2. Within an incredibly short, aggressive time frame of just 36 months, the macroeconomics of global computing are going to fundamentally flip.
Because the vacuum of space offers pure, uninterrupted solar power and completely eliminates the massive capital requirement for heavy, degrading grid-scale batteries, putting AI systems in high orbit could soon be a staggering 10 times cheaper than running them on Earth.
And number 3. Actually executing this transition from Earth to space requires an unprecedented, almost unimaginable scaling of global industrial logistics.
We are talking about 10,000 massive Starship launches per year, which breaks down to one launch every single hour, and the necessary creation of massive new terafabs to manufacture the microscopic silicon hardware on a scale the world has never seen before, all simply to solve the cascading whack-a-mole bottlenecks of power, launch, and production.
Before we sign off today, I want to leave you with one final, highly provocative thought to mull over, building directly on the implications of what we've discussed. We have spent an hour talking extensively about the engineering physics, the battery chemistry, and the logistics of moving the primary engines of human intelligence, corporate data, and global compute into low Earth orbit.
But consider the massive geopolitics of this new reality.
If the most powerful AI systems in existence containing the world's most sensitive enterprise data, military secrets, and the core algorithms driving the global economy are physically located in space, who actually governs them?
When the world's intelligence sits in orbit, freely floating above all sovereign national airspace, it completely rewrites the rules of global jurisdiction, data sovereignty, and international security.
You are no longer dealing with data centers securely located within the borders of a specific country, subject to specific national laws, search warrants, or taxation.
You are dealing with an incredibly powerful orbital infrastructure that essentially exists in a legal and regulatory void. How humanity navigates the governance, security, and ownership of a space-based light cone of consciousness may prove to be a far more complex challenge than engineering the rockets to get it there.
That is a phenomenal point, and exactly the kind of paradigm-shifting late-night question we love to explore on this show. It is the ultimate Wild West.
Thank you so much for tuning in to this deep dive. For more rapid-fire insights into the tech that is shaping our immediate future, don't forget to check out the Bite-Sized Tech News TLDR YouTube channel for our daily video updates. Keep questioning the physical limits around you, keep learning, and we will catch you on the next one.